Hi, I'm Reza Lame, and it is the fourth video of my tutorial how to model a prestressed concrete beam using ANSYS Mechanical APDL. The first video was about geometries, and the second video was about how to define the basic specification of your structure and how to mesh and some basic option to create your models. And in the third video I discussed about how to model your contacts, and I provide you two options to model the contact between two segments. And in this video I'm going to just focus on my tendons, on my prestress tendons, and how to model the interface between my prestress steel and my concrete, and how to apply a pretension on my prestress cables. As you can see, there are two sets of tendons in this structure. These two tendons are my external tendons, and it means that they don't follow the strain and stress of my concrete. But these three tendons are bonded and internal, and they pass all along my concrete, and they follow the strain and stress of my tendon and my concrete, and they have effect on each other. And it means that the stress of the various part of my structure for my tendons varies. For example, in this part I may have greater stress than these parts, but in these two tendons and this unbonded and external tendons, the story is different, and the stress just change in the position that I have a deviation in the path of my tendon. I want to start with my internal tendon, and these two internal tendons are here. I choose a good view here. I have these two tendons are different because in this tendon my nodes are exactly at the same place of my the node of my concretes, and in this tendon the nodes are not exactly at the same place. For example, I want to start with this node, and the node of the location of my tendon must be here, so I have to shift my mesh and my concrete nodes, or define a constraint equation or something like that to define this interface. I have three options to define the interface between my concrete and my prestress steel. These three options are here. One of them is merging, the other is coupling, or and using constraint equation and adjacent region. I want to start with merging. For example, this is a good tendon to merge. Merging is exactly like the same I did for my segments. You saw that I have some segments and some volumes in this part. They were discreted, and using this menu and merging item, I unite some nodes in their interface and make this segment as a monolithic part of my structure. And again, I can do the same for my tendons and my concrete. Again, a good view. As you saw before, for my segments, I have to select the nodes first if I want to use merge items. So I want to here select the nodes of my concrete and my tendons. Here, these two pair of nodes are my concrete and also my segments. But I have a problem here. Here, this is a good view, and my volumes. I have three joints in my structure, and in the location of my three joints I have three nodes. One node is for one of my segments, and the other for the other segment, and the third node is for my cable. And if I use merge items, all three nodes become a single node, and it means that the node of my, for example, first segment and the second segment become a single node, and a bond may form between these two segments, but there is no any bond in the location of my joints between two segments. In order to avoid this, I have two options. For example, I can unselect all three nodes, if I show you here on select box, you can see I have 3 numbers, node numbers here, again 3 numbers, again 3 numbers. I can unselect, and if I want to, for example, I want to select one of these nodes, I have to unselect one of the nodes of my segments, and the node number and the node of my tendon must merge with one of these segments, not both of these segments. So I have to unselect one of these 3 nodes that's related to one of my segments. But I want to unselect all 3 nodes, and I here I press OK and plot nodes. My nodes are ready, so I can merge my nodes. Plot, but another point remains. These 2 nodes are not exactly at the same place, and if I merge these 2 nodes, these 2 nodes become a single node, and it means that my mesh will be altered. But the position of the new nodes is a question, because we don't know that the new node will be become in this part or in this part, or a place between these 2 nodes. And the answer is here. If you choose one of these options, lowest or highest, the node number of your new node become the lowest number, and also the place of your new node become the place of the node with the lowest number. And I want to choose highest number because I know that the node number of my tendons are higher than the node number of my concrete, and I want to alter this mesh and also change the location of my the nodes of my concrete to be shifted to the place of the node number of my tendons. So I choose the highest number, and I ensure that my node number of my tendons are higher because I meshed my tendons after meshing my concrete. And a range of tolerance must be inserted. I insert, for example, 10, but if it don't work, I can increase to reach the solution. Plot elements. You can see that my mesh has changed, and it worked because I choose the highest number. This tendon remained, and I want to choose another option to model the interface for this tendon. And the other option, as I told you, is coupling. So I have to, again, for coupling, like this thing I told you before, for my joints and sliding of my joints, I have again select the nodes here, plot, okay, plot node, and also I have the same problem for my joints, plus plot volumes. Again, I have to unselect nodes box, okay, plot nodes. But in this case, my nodes are exactly at the same position, so I can use coupling. Again, I use coincide because the nodes are exactly at the same place. If I choose all appropriate, the nodes of my concrete and the node of my steel will be coupled together in all translation degree of freedom, UX, UY, and UZ. If my tendons are bonded and have a connection with my concrete, I choose all appropriate. you can see some green points and green signs here. This means that my coupled set have been created. Plot elements. But sometimes you want to model the bond between your concrete and your prestress steel really exact. And you know, when you are for merging and this item, you consider your bond between your concrete and steel really ideal. And it means that you ignore the sliding between your prestress cable and your concrete. But in reality, there is a slide between your concrete and your steel. So you have to model this interface more exact. You have another option here. Again, you have to do coupling, and you have to couple your node. I want to delete the coupling set. In this part, you can delete your coupling set. This is the first node coupling set, and it is the second coupling set. But don't forget that you have to choose any are selected and delete these coupling set, because you have another coupling set for your contacts. So I choose here, plot nodes again. Okay, plot nodes. So again, you have to do the same for your X and Y direction, and you have to couple the nodes at interface using coincide node for your X and then Y direction. Your Z direction is the direction of your sliding, and you want to model the exact thing really exact. So you have to define a set of spring to model the sliding, and it means again like the same you did for your contact. Again, define an element like combine 39 again. Here combination 39. Okay, options, you no need to change this part, and you choose here UZ and okay. There's an exactly the same video for modeling the bond between concrete and steel by an Arab user, Ala STC. You can refer to that video. It was very good and useful, and in that video it discussed completely about this topic. But I want to summarize the points of that video for you here. Again, you define, and here you in real constant, again you have to choose here, and the force and displacement. You have to define the force and displacement and calculate the force and displacement. You can refer to an experimental study that they, for example, they draw a tension and a strain and stress and the shear stress for the bonding between concrete and steel, and you have to, for example, calculate those items using because there are tension and strain, and you have to transform the tension and strain to force and displacement, because you have a spring here. For example, you have to multiply the tension to the area of your tendons and the length of your element, and multiply all of them to reach a force and displacement. Then insert the force and displacement here, like here, for example, 1000 or another data you will be calculating. Okay, and close. And like the same I did here, modeling, create elements, auto numbered, true nodes. Oh, excuse me, we have to define the attribute, material type and real constant, for example, and do the same thing I did for my joints. Choose these nodes and press OK to create the spring elements. But I don't want to model these such exact calculation for my bond, and you can refer to that video. It completely discuss about this point. And these two tendons are remained. These are my external and unbonded tendons. And the third option is really useful, because sometimes in these two tendons the node number of my concrete and the node number of steel are exactly at the same position or approximate to each other. So I can choose some items that use coincide nodes, like merging items or coupling at coincide nodes. But sometimes the node number of your steel and the node number of your concrete are not exactly at the same position. So you have to choose another option to do this. And this option is again in coupling as CEQ and is in constraint equation. You can, for example, define a constraint equation with this pattern. But writing a bond using this pattern looks complicated, because you have to know about the constraint and also define a constraint equation that meets the needs of your bond. But there is another option, this adjacent region, that do this for you and automatically define a set of constraint equation for your nodes and elements. If you see the help about this command CINTF or constraint equation, it will create a set of constraint equation for the nodes you select and the elements nearby those nodes. So usually the nodes must be from the elements with more dense mesh, and the elements must have greater mesh size. For example, in my concrete and steel, I have to choose the nodes of my steel and the elements of my concrete. After I select all of the nodes and elements I want, I can apply these and assign these degrees of freedom and then press OK to create constraint equation. You have 6 degrees of freedom here. For translation, I need just translations UY and UX UZ. But before I apply this command, I want to select the nodes and elements. I want to first select nodes by attribute, elements by attribute, material number 3. Okay, select entities, nodes attached to elements. Okay, plot nodes, and in this part plot lines, just these two elements. Select entities, nodes, reselect box. Okay, plot nodes. So these are my two nodes and elements by attribute, my concrete elements. So my material number must be 1. Okay, plot elements. And then I want to press adjacent region and degree of freedoms ux, then uy, uy. And for uz I don't want to insert anything because my sliding and also my tendons are unbonded, so there is not any hindrance or any barrier for my strain and stress along a z direction, so that must be empty. Then press OK, plot nodes. You can see here some purple signs in this part. Select everything, plot nodes, and also there are 6 sets of purple signs because the nodes are related to the nodes of the concrete elements. So I define my interface between my concrete and my unbonded steel, but at the end you must bond your tendon to your concrete and close your tendon because your tendons are open from this end and also this end. In this end I will discuss about the boundary condition, and you have to close this part using boundary condition. But in this part again you have to do the same and merge the nodes by unpick from full box. Okay, plot nodes, then again numbering, merge items and nodes. Select everything, plot elements. So the interface between my prestress unbonded steel and my concrete has been formed. In this part I'm going to move to applying the prestress force on the steel. Again you have 3 options to apply the prestress force on your steel. The first and second option are somehow the same. There is a comment here called in state. It will apply an initial stress or strain as you want on your structure. Initial state, and there are some examples, and you can use these examples for your coding. I can apply initial stress or initial strain. First I have to choose the elements that I want to apply this stress. Material number 3. Okay, plot elements. These are my elements, and also I can choose also the nodes in order to ensure that it will apply just on my tendons. Plot elements. So I have here some options here. Initial stress on whole model, or for example initial stress statement, initial stress on material number 3. For example, the thing is I need is really is exactly the same. Here I see, because my material also is 3. For example, I can apply here. I can copy and paste this part here. For example, in this part, then this part. For example, I want to insert 500 megapascals. And if you want to again change it to 0, you can here change it to 0. But based on my personal experience, initial stress will not work well and will make some problem for you if it passed the yield stress. And initial strain usually work better. And this is the initial stress, the normal initial stress, strain command, and you can copy and paste this command or this pattern for your initial strain. And you have to, for example, transform your initial stress, based on your details and your plans, to initial strain. It's stress and strain using elasticity modulus. You can transfer it to them to each other. So for example, I want to apply and stress equal to 100 megapascal. So 100 megapascal, so the strain must be 0.005. So I press enter. This is the second option you have. But the problem with this option is that it will apply this strain first place, and it will not gradually apply this strain on your model, and it may make some problem for your solution and your convergence. So I have even another option to apply this strain gradually, and it is somehow deceiving the software, because I'm going to apply a load, and instead of applying the initial stress or a strain, I want to apply a temperature on my tendons. So apply here a structural temperature on lines, for example, on lines, for example, lines, these two lines. You have to choose the lines, no matters. Before I have to choose the lines, select entities, lines, attach to areas, unselect, okay, plot lines. Or for example, select entities, lines, by non-peak, unselect, okay, box, unselect those lines, plot lines. So these are my lines, and I can apply a temperature on my line. Okay, temperature. But it will not work, because before I apply the temperature, I have to here go to material properties, because I didn't even define any coefficient of thermal expansion. And in structural thermal expansion, second expansion, isotropic, you can apply a coefficient of thermal expansion. These two are the basic equation for strain. This is the elastic equation, and it is the thermal equation. And using these two equations, we can reach to this equation for alpha. I want to apply alpha in a way that if I apply 100 centigrades as temperature on my lines, it will lead me 1000 megapascal for my tendons. So I know the elasticity modulus and know these two values, and if I calculate, I can reach to this number. And then I press OK, and now it is ready to apply temperature on my lines. Structural temperature, lines, box, Okay, then 100. Okay, so that's it. I apply 1000 megapascal on my on my tendons. But plot elements, based on my personal experience, the second way and the third way are best to apply pretension on your tendons. It means initial strain and temperature. And the temperature is better because it will apply the load gradually. But if you just apply temperature, in some cases you will may face problem, because the connection between link elements are literally hinged, and you have lots of hinge in a direction, and it means that your cables are not stabilized. And if there isn't any load on your tendons, they will be unstabilized. And if you press, for example, on solve, the software will show you an error about your structure that is not stabilized, and it cannot solve this structure for you. You can divide the pretension. For example, you can apply 10% of your pretension stress using initial strain, and the other 90% using temperature. That's it for this video. I will explain about the boundary condition and your supports and the solution option in the next video. Thank you for watching. Don't forget to subscribe.